Welcome back. Today we're going to talk about conics, the first part, and we're going to focus specifically on parabolas and ellipses. So let's talk. First of all, let's talk about what conic sections actually are. When we look at this diagram here of a conic section, we're looking at two cones that are put together on the end. So two ice cream cones that are sitting with that, that little part at the bottom that's got all the chocolate in it. The two pointy ends are together. And if we cut it with a plane that goes through a side and the bottom, this part here forms a parabola. So that's our first one. An ellipse is formed by a plane that goes through the two sides of a cone. And as you can see, it's kind of this oblong shape. A circle is cut by a plane that's parallel to the base. So the base of that cone, if we cut it parallel, we're going to come up with a circle. And a hyperbola is made using both of them, a big plane that goes through a section of both of them. And as you can see, it forms this two-parter curve that's got some asymptotes in the middle that we're going to talk about as we get into more of the conic sections. So those are the four basic conic sections that we're looking at. When we get into this, we're going to start talking about parabolas. Let me make this window a little bit bigger. And with parabolas are a set of points, just like any graph, and they are a set of points that are equidistant from a fixed line called the directrix and a fixed point called the focus. The vertex is the midpoint between the focus and the directrix. And so the standard form of equation with vertex at 0, 0 and a directrix at y equals negative p is going to look like this. But first I want to draw a diagram and kind of show you what's going on, because this verbiage can be a little bit confusing at times. And so let's start with a coordinate plane and a parabola that looks like the one that we normally see. Okay, it's just a bowl, could be a bowl that opens down. And so our vertex, in this case, is at 0, 0. It could be anywhere, but we're using 0, 0 because it's an easy point of reference. And so when we look at the additional points that we're talking about here, we need a fixed line and we need a fixed point. And so I'm going to put these onto this graph inside of the bowl. Important to remember that. This is the focus. And the focus is a certain distance from the vertex. Okay? In this case, the focus is at 0p, meaning it is p units up on that y-axis. Well, that is the distance here from the focus to the vertex. Well, notice, it's the midpoint, and so if I go down another of that same distance, p, this is the fixed line known as directrix. It goes through here. And it's y equals negative p. How do I know that? Well, if this distance is p, then this point down here has to be at 0, negative p. And if it's a horizontal line that goes through one y value, then that's got to be the equation of that line. And so what are we looking at here? We're looking at these distances from the focus to a given point, x, y on my curve, and this distance to the directrix are going to be the same. So these distances are the same from here to here. Well, what does that mean? Well, that means that each point on this line, if I were to draw a point and then to the directrix, are going to be equidistant from both of those things. Okay, so my equation for a parabola that looks like this, opens up or it opens down, is x squared equals 4py. P cannot be equal to 0, okay, because the distance to the focus can't be 0. That's that p distance there. Second diagram. It's going to open the other way, and you're going to see some striking similarities, because really it's just this other diagram turned on its side. So I am going to, in many ways, replicate it. Here's my vertex. It's at 0, 0. But instead of the focus being up here, the focus is still inside the bowl. And its coordinates now are p, 0. Why the switch? Well, the focus is now on the x-axis, and so that's got to be the x-coordinate. Well, if this distance is p, and I go p this way, this has to be my directrix. Except now it's an x equals negative p, because this would be negative p comma 0. And an x line goes up and down, right? And so my distance that I'm measuring x and y is going to go from my focus to my directrix. And these are going to be equidistant, okay? That's the basic gist. So the equation for this one is y squared equals 4px. Notice, oh, p still can't be equal to 0. Notice, this is the one that opens up or down, meaning it's the normal one. It's got the x squared in it, like the y equals 4x squared, etc., etc. This one's the other way. It's flipped on its side. It's not going to work to do the x squared, so we got to have that y squared portion there. All right, so that's the immediate explanation. I'm purposely leaving these equations up here as we do example 1. So we're going to find the focus of the parabola whose equation is this. Well, notice, in both of these equations, the squared term is by itself. In mine, the squared term is not by itself. So I need to solve to get an x squared by itself. So what I'm going to do is I'm going to start with my original equation, and I'm going to solve for my squared term. So in this case, x squared equals negative 1/2 times y. And I did that by turning divided by negative 2 and 2 multiplying by 1/2, because both of these have to do with multiplication. Okay? And so in this case, I see my x squared term here is equal to 4py. Well, look at this. X squared is equal to negative 1/2 y, but x squared is also equal to 4py. And so in this case, I can set those equal, because I'm trying to solve for what x squared equals. And so what I can do is, I'm going to multiply actually I'll divide both sides by 4 to start. I was going to say multiply by negative 2, but we'll do it this way. It works out the same. So negative 1/2 divided by 4 is the same as 1/2 times 1/4 equals negative 1/8 equals, so negative 1/8 y equals py. If I divide by y on both sides, move this up now, negative 1/8 equals p. Well, what does that mean? Well, that means if I look at my graph, okay, if my p is at negative 1/8, that is my focus. So if I draw my parabola here, it's got to open down because my focus has to be on the inside. Well, notice I've got a negative, so I knew that it opened down. But also, my directrix would be up here at 0, 1/8. So my directrix, they didn't ask me for this, but they could have, is y equals 1/8. Okay, so that's how that works if we're finding the focus. Let's work on another example. So let's find the focus of a parabola. Write the standard form of the equation of the parabola with the vertex at the origin and a focus at 2, 0. Let's look at what we got here. Drawing my coordinate plane. My focus is at 2, 0. So that's over here. Notice not 0, 2, so 2, 0. And so I've got a parabola that opens this way, right? Think in my head what that means. It's not the x squared. It's got to be the y squared one. So y squared equals 4px. Start with that equation, and then let's look at what we've got. So if this is 2, 0, that means my distance from my focus to my origin, focus to my origin, but in this case the vertex is 2, and so my distance to my directrix is also 2. Why is that good to know? Well, that means that I just kind of understand my topic. And so if this distance is 2, then p equals 2. Well, what does that mean? Y squared equals 4 times 2 times x, so not 8x. Y squared equals 8x. And so what I can do is I can write this as my standard form because I've got 4 times p times x. That's all there is to it. Using those distances and what I know about these curves and these shapes to find my equations. Ellipses. This is the last topic that we're going to talk about. Today we're going to talk about ellipses in terms of the set of all points x, y in the plane, the sum of whose distances from two fixed points, foci, is a constant. Okay, so what does that mean? That means the distance, so this is a focus here, this is a focus here, okay? And so the distances to x, y, so A is the distance from focus 1 to this point, B is the distance from focus 2 to this point. A plus B is always the same. So no matter where I move around this curve, if I drew another point here and I had these two distances, it would be the same sum as these two up here. Okay? A couple things to note about ellipses. This is the major axis, the long way, and this is the minor axis, the short way, the squat way. Okay? Along the major axis, that's where the vertexes are, vertices. And this is a vertex. Okay? Center, obviously, we know what that is. Okay? That's the basics of an ellipse. Let's look at the equation. So if the center is at the origin, let's look at a couple of pieces of information. If I draw in this ellipse, this is, again, going to be another one of those cases where we have two parts. If I've got my points in here, along my minor axis, these are going to be A, B, and C. Okay, and so where these intersect this y-axis, or where those turning points are going to be the B's, and these out here are going to be A0, negative A, comma 0. So to look at that means that the A is going to be the longer one because it's the major axis, and the B is going to be the shorter one, it's the minor axis. My foci in here, the two foci, are going to be at my C coordinate. So this is negative C comma 0, and this is C comma 0 in here. These are my distances that are always going to have a sum of the same. Okay, and so my equation for one that has its major axis going horizontally is going to be x squared over a squared plus y squared over b squared equals 1. So notice, in this one, my bigger number, my major axis, goes with my x because that's where it's bigger. In my other diagram, my major axis is going to be along my y, and so my equation is going to go x squared over b squared plus y squared over a squared equals 1. Strikingly similar, but where is that major axis? Major axis horizontal, it's got to be the A. The x goes with the A. So the x goes with the longer one, and this one, the B, okay, goes with the shorter one, so the A goes with the y because it's longer. Same thing here. Negative B comma 0. B comma 0. So my A's and my B's are along here like this. So in this case, my B's are going with my short one. Why? Well, they're going on the short axis. Okay? So they're going on that short axis. So when I have my C's here, notice everything just switches around whether it's in the X position or the Y position. That's one piece, is knowing the equation. For ellipses and hyperbolas, the other piece is this. A, B, and C are also related by the equation C squared equals A squared minus B squared. Okay, so that's going to be another piece that we have that relates these distances here. Okay, let's remember these two things. Purposely keeping the equations and this piece of information up here. So let's look. Find the standard form of the equation of the ellipse that has a major axis of length 6 and foci at negative 2, 0, and 2, 0. I've already drawn in an ellipse here. Excuse me. If my major axis is 6, that means there's 3 on either side. Well, what does that mean in terms of these coordinates? These vertices are going to be at -3, 0, because my origin is my center. And my foci are at -2, 0, and 2, 0. Well, what does that mean? If you think back to what we talked about earlier, I need an equation. My big axis, my major axis, is with my x. And so here's my equation. Well, what pieces do I need? I need an a and a b. Where did those come from? Well, my a and my b come from the coordinates of my points around the edge of the ellipse. Well, unfortunately, I know my a. This is a here. So a is that 3, that distance 3. And so x squared over 9 works. Plus y squared over b squared equals 1. Well, unfortunately, I don't know what b is. And so that's where I have to use this part here. Because I do know c. Okay? C is here. This is c. It equals 2. This is a. And so if I use this equation up here to say c squared equals a squared minus b squared, then I can say 2 squared equals 3 squared minus b squared, because I don't know b. I don't know what this is here. Okay? So 4 equals 9 minus b squared. And so if I simplify, -5 equals -b squared divided by -1. 5 equals b squared. And so b equals square root of 5. It's a distance. Okay? So this is my square root of 5. And so when I put it on bottom in here and square it, that means b squared equals 5, because it's square root of 5 squared. So what's my equation? My equation is going to be x squared over 9 equals, x squared over 9 plus y squared over 5 equals 1. How do I know? My major axis under x. My minor axis under y equals 1. Okay? That's all there is to it for that. Sketching an ellipse. Sketch the ellipse given by this equation in this coordinate plane. This doesn't look like anything that we've done, but the problem is it does not equal 1. And so I need it to equal 1. And so what I'll do is I'll divide by 36 on both sides. You're going to see what happens. So it equals 1 on this side. Over here, 4 over 36 is the same as 1 over 9. So I got x squared over 9 plus y squared over 36. My bigger number is underneath my y, which means it's going to be up and down. Okay? So now, if this is, and this is, the answer to a squared problem, so this is x squared over b squared plus y squared over a squared equals 1. 36, if 36 is a, then a has to be equal to 6. Why? It has to be. How do I know? It has to be 6 because 6 squared is 36. B is 3. And so my major axis is 6 per side. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Minor axis is 3. 1, 2, 3. 1, 2, 3. It's good. Check that out. Okay? And so these points come out of this equation, and the equation is found by setting it equal to 1 by solving to get it equal to 1. All right? That's all there is for today, guys. Thanks for watching 4.4a on the first part of Conics, and we'll see you next time.